Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The next talk, I want to introduce our next speaker, Nadia Henninger. Nadia is an assistant professor at University of Pennsylvania now. She was previously an NSF postdoc at UC San Diego and a visiting researcher at Microsoft Research in New England. She works in cryptography, applied cryptography, algorithms, and security. Her most popular work was in identifying entropy problems in cryptographic keys on the internet, which got her 2 Best Paper Awards at Usenix Symposium. She received her PhD at Princeton, and before that she was an undergrad at Berkeley.
Thank you very much for inviting me. It's exciting to be here. I am sad about the warped slides. I just redid them in 16:9 trying to avoid this problem, but I guess computers are hard. In this talk, I'm going to talk about, actually using lattice basis reduction for cryptanalytic purposes for the most part. And I've called this approximate common divisors via lattices. I'm going to actually introduce the approximate common divisor problem and sort of the framework of using lattice basis reduction to solve polynomial equations modulo divisors, and then talk about a number of extensions of this idea to different realms. So sort of as a little bit of background, if you consider the general problem of solving equations modulo n, where n is some integer, if n is prime, then we know how to do this efficiently. You can compute roots of univariate polynomials in polynomial time, modulo primes. And if n is composite, the best thing that we know how to do in general is to factor n into its prime factors, and then solve the equation mod each prime, and then use the Chinese remainder theorem to lift to solutions mod n. So this sort of general question is of great interest to cryptography. In general, solving a quadratic equation modulo n is actually as hard as factoring n. The Raven encryption system is based off of this fact. Of course, the RSA encryption system is also based on the assumption that solving the equation x to the e, where e is the encryption exponent of RSA, minus the ciphertext, finding roots of that equation, mod n, should be, we hope, as hard as factoring. The entire internet depends on this fact. So we hope in general that this equation, that solving equations mod n is hard if we don't know how to factor n. And then even if we do know how to factor n, there might be a little bit of difficulty in enumerating all of the solutions because there might be exponentially many solutions if n has very many prime factors. So this problem might be hard in a few different ways. So sort of the motivating theorem starting this talk is a theorem due to Coppersmith, which tells us that in some situations we can actually find roots of equations modulo n. And so if we're given some polynomial of degree d and some integer n, and we want to find the roots of this polynomial, we want to find some root of this polynomial mod n, Coppersmith's theorem tells us that we can do this if the root is small, where small means of size n to the 1 over d. So, okay, and in some sense you can think maybe this is a natural bound to have, because if you take your the RSA equation x to the, call this d minus c, if c has some root over the integer, so we just remove this part, then we know how to solve this equation because it's just factoring polynomials over the rationals, which we can do efficiently. So if c has some root of size less than n to the 1 over d, so this mod n just goes away, then we can solve this equation. So what Coppersmith's theorem is telling us is that even if there are some large coefficients involved in this polynomial, we can still find its roots. we can sort of get rid of the large coefficients and do the stupid thing. So as I said, why is this theorem interesting? So there's sort of two effects. By accepting some bound on the size of the root that we're looking for, we can provably find solutions to polynomial equations in polynomial time without factoring n. So just forget about the fact that we don't know how to factor n. We can still find some solutions of the equations. The other implication is that maybe n is not an RSA modulus. Maybe n has very, very many prime factors. And this actually is a sort of constructible proof that there are only polynomially many small solutions to a polynomial equation. There might be exponentially many solutions in general, but within this range of size where Coppersmith's theorem applies, then there are only polynomial many solutions, and we know there are because we can enumerate all of them in polynomial time. So how does this how do we actually accomplish this goal? So the big sort of insight here is we're going to take our input polynomial f, and we're going to take our modulus n, and we're going to try to construct some new polynomial q with the property that all the roots that we're looking for of f mod n are actually roots of q over the integers. And then once we've constructed this magical q, then we can just find the roots of q over the integers, check whether they actually vanish mod n, and if they do, then we accept them as a solution to our problem. So the sort of main lemma here is the fact that we know that, okay, so somehow we're going to ensure the fact that q vanishes mod n at the roots r that we're looking for. If q also has the property that its coefficients are small, where small means that if we add up the size of the coefficients, there should be a to the I power here. So if we add up the size of the coefficients and sort of the maximum size that the root could have, if that is strictly less than n, and we know that q vanishes mod n, then q actually must vanish at r over the integers. So then we're done. So how are we going to achieve the two properties here that we want in our out of our q? Well, to ensure that q actually vanishes mod n, if we construct q as an integer combination of our input polynomial and multiples of n, then any integer combination of these two things will also just vanish mod n when we plug in r. So that works. And in order to ensure that q has small coefficients, we're actually going to take these polynomials, consider them as coefficient vectors, construct a lattice generated by the coefficient vectors of these polynomials, and find a small vector in this lattice. And that small vector will correspond to a polynomial with small coefficients. And we just treat that as our polynomial q and factor it to find its roots. And I've been lying to you here slightly in that if you're considering Coppersmith's theorem, this vanishing mod n doesn't actually work. But if you take higher multiplicity, so instead of asking to vanish mod n, you ask to vanish mod n to the k, which you can achieve by taking powers of f and n of this form, then you can actually achieve a theorem. So this actually works. So here's sort of the complete outline. To make things concrete, so we input our f and n. We're going to construct a matrix of coefficient vectors of powers of f and n. So n to the k. K is some magic value that comes out of the analysis. Then say x n to the k. We start including powers of f up to f to the k. Some powers of f, multiples of x higher than that, and so on. So these are all elements of the ideal generated by f and n taken to the kth power. And then once we have this matrix, then we're just going to run a standard lattice basis reduction algorithm. We don't need any special properties out of it. So if we just use the LLL algorithm, then as we heard about in Damian's talk just before, we get some exponential approximation factor, and we get the promise that our vector is about of size determinate to the 1 over dimension. Then once we find a vector of this size, then we will construct a polynomial out of that vector, factor it, find its roots. So you might be worried, well, what actually happens in this exponential approximation factor? Is this going to destroy the theorem? And one of the magical things about this sort of Coppersmith method is that in this case, the exponential approximation factor actually disappears in the analysis. So it just becomes a constant, which you can get rid of in polynomial time, which is one of the sort of magical things about Coppersmith's method, is that an exponential approximation factor is okay. The other question you might have is this sort of heuristic. Are we hoping that we'll find like the shortest vector? And it turns out that this is completely provable. So once we find a vector with the approximation guarantee, then we're set. So sort of magical theorem. Here's a concrete example, just in case you were, I don't know, feeling confused, or if you, like me, like practice. This is not just a theoretical method. It totally works really well in practice. So here is, let's see, I'm going to generate an RSA modulus. This is kind of an embarrassingly small RSA modulus, but I just wanted to like have something that would fit on the screen. So ignore that part, because it still works if I take a 2048-bit RSA modulus. And then I'm going to construct my message, and my message will be the password for today is swordfish, and this is just I'm converting it into an integer, so forget that part. And then I'm going to encrypt my message with RSA exponent 3. So I raise my message to the third power mod n. So imagine that for some reason I know that I am the attacker now, and I know that the ciphertext has the form the password for today is something. Then I can then try to apply Coppersmith's method to discover what this secret password is. So I construct some value. This is actually the bound on the size of the root that we're looking for. It's about the right size. I construct some matrix. I didn't include that part in the slides because it's kind of long, but essentially m is the coefficient vectors of n squared times x, n squared times x squared, and so on, and then a bunch of multiples of the polynomial a plus x minus the ciphertext. Then I apply LLL to my matrix, and then I take the smallest vector in the LLL reduced basis, I reconstruct a polynomial out of that, I factor that, and then if I subtract this value from A, then I get the actual message. So this is actually an example from Coppersmith's original paper. It's the problem of stereotyped messages. So this is why RSA padding is important. Okay. The variant of this theorem that I'm actually going to talk about for most of this talk is actually a version which is in this form due to Howgrave-Graham. So the question that I'm going to consider is, instead of trying to solve equations modulo n, I want to actually solve equations mod some divisor of n. So remember, I still don't know how to factor n, so I don't actually, if I could factor n, then I could just, I don't know, try to solve mod each divisor. But here I'm just going to say, okay, I want to find solutions that happen to vanish mod large divisors, where I'm measuring large by some parameter beta, which is between 0 and 1. And this theorem tells me that I can find solutions to the equation, which is essentially, this is a degree 1 equation, x minus r, or a minus x, sorry. And I want to find a solution to this equation that vanishes mod some divisor of n. And this theorem says that I can do so if my solution is less than n to the beta squared in polynomial time. So as I said, this is sort of a generalization of Coppersmith. Here I'm specializing to the equation of the form a minus x, and I want to find solutions mod this divisor, but the algorithm and proof are essentially identical to what I showed you in sort of Coppersmith's original theorem. And if you want to, you can write this in general. You get a bound of n to the beta squared over d if you have a degree d equation. You can also say, well, maybe I don't have an exact I don't have an exact multiple of this divisor. Instead, I just have two approximate multiples of the divisor, a1 and a2. And I can actually still solve this. I take a little hit in the size of the equation that I can or the size of the root that I can find. This one is actually heuristic. Okay, so what is this good for? Sort of the, I guess, canonical, useful application of this theorem is for factoring with partial knowledge. So here I'm generating some RSA modulus again. I have two 512-bit primes, P and Q, so I have a 1024-bit RSA modulus. Then I take this value A, which is some, it's near P. So I'm basically just subtracting off a little bit so that the least significant 86 bits of P have been transformed to 0. And then I assume, okay, I as the attacker have access to this value A with 86 bits of P missing. So what do? I construct a matrix which is basically powers of, or it's multiples of, I have n, I have the polynomial a plus x, and then a plus x squared. And then I run LLL on this, this basis of my lattice. So this is a 3x3 lattice. I take the polynomial generated by the smallest vector. I factor this. The first root that I get, if I add it to A, is equal to P. So this works. And actually, for those of you who are going to AsiaCrypt, I have a paper with Dan and Tanya who are sitting in the back. And we actually use this to break real live RSA moduli that people were actually using in practice. So Coppersmith Theorem, practical. Okay.
How do you get the difference if it's the last 86 bits, the first 86 bits?
No.
No.
So if it's the first 86 bits, then you construct the equation like, you know, whatever piece you know plus like x times, you know, 2 to the some power that gives an offset. And you just want to find roots of that equation. So you can put the 86 bits anywhere in the middle. And this is less powerful than this theorem because if you want sort of the exact n to the beta squared, then you need a much larger lattice. So this example is taking a very small lattice that gives you a worse guarantee. So
do they have to be consecutive?
If they're not consecutive, then you can take chunks and you can try to solve, okay, I have, you know, some variable representing this chunk, some variable representing this chunk, and then you get, you know, a new variable in your equation. You have like some linear equation. Alex May has a paper in AsiaCrypt several years ago sort of doing that exact variant. And I guess I have a paper doing the variant where you have non-consecutive chunks. You just have a bunch of errors in your RSA modulus, but you need extra information for that. In general, sort of extending to the multivariate case is not as well understood. So I want to talk about a slightly different variant of the multivariate case, which is if, yeah? Right on the board. Okay. So if you have a bunch of different chunks, say like this is P, and say that here's one chunk you don't know, and here's another chunk you don't know. Here's another chunk you don't know. Call this X times 2 to the, say, T, Y times 2 to the S. So here's like offset T, offset S. This is offset U, so you have Z times 2 to the U. Then you could do this by you could solve this by writing some equation of the form, say A plus X times 2 to the T plus Y times 2 to the S plus Z times 2 to the U. And this should be equal to 0 mod P. This should actually just be equal to P. So that's one form of the equation. Or this is one form of sort of a multivariate extension of this. The multivariate extension that I want to talk about is the case where we get a bunch of near multiples of P. So this is essentially that we have like P plus R1, P plus R2, A1 equals A2 equals P plus R2, and so on. And you can add multiples here too if you want to. So the problem here is if you're given a bunch of sort of near multiples of P, can you reconstruct P? Can you do any better than if you just have one near multiple of P, which was sort of the original variant that I was talking about. So here, if I subtract off sort of A1 minus R1, A2 minus R2, and so on, and I take the GCD of all of these things, then I want that to be equal to, say, P, which should be larger than, it's bounded by some power of n. So this problem actually arose recently in the context of constructing fully homomorphic encryption systems. I don't know how much we will hear about fully homomorphic encryption today, but in general, I mean, fully homomorphic encryption, you want to do arbitrary computation, say, in the cloud on encrypted data. And the original schemes and most of the work has been constructing fully homomorphic encryption based off of, say, hard problems over ideal lattices or LWE, but there's also a number of works trying to construct sort of simplified fully homomorphic encryption systems, which use assumptions over the integers. And the assumption used in all of these works is essentially that the approximate GCD problem is as hard if you're given a whole bunch of inputs as if you're given just one near multiple of P. So already we know we can do better than brute force for this problem, but this is a sub-exponential algorithm, so the question is exactly how hard is this problem? So if you sort of take the insight of like what does Coppersmith's method actually tell us about this problem if we try to just take the stupidest possible extension of this to the multivariate case. Basically, all of the theorems here, the proofs look exactly the same. The question is just sort of, how well can you do the analysis to balance the parameters? So the natural thing to consider is, we're going to, we now have a bunch of different solutions that we're trying to find. So we have these R1 and Rm. These are all variables that we're trying to solve for. So instead of constructing a single polynomial equation in one variable, we're going to try to construct a series of polynomial equations in m variables, and then solve, and we're going to construct them so that those all vanish at the roots that we're looking for over the integers or rationals. And then we're going to, well, how are we going to find these? We're going to look for these in, say, the ideal generated by each of these polynomials in our different variables and n, and we're going to ask for it to vanish at some high power of our approximate common divisor, and then we're going to solve the system of equations to find the roots. This is sort of the cartoon version of what we would expect an algorithm in this framework to look like to solve this problem. So what actually what's the difficulty here? Like, why can't you just do this? One problem is that, so we're going to construct some giant lattice, and we actually need m equations rather than just one equation. Well, it's okay. We actually know that we can find m relatively short vectors in a lattice just from the approximation guarantees given by LLL. So, okay, this becomes some 1 plus little of 1 factor in the exponent of the theorem statement. And actually in practice, you can just ignore having to do this complicated analysis because a random lattice, basically, if you run LLL on a random lattice, all the vectors have approximately the same size. And I'm using a slightly worse approximation factor here than Damian gave, but this is what my lattices look like when I just run a fast LLL on them. Okay, so approximately all the vectors that will come out are about the same size. Apparently LLL can't tell the difference between my special lattice and a random lattice. The next problem is, okay, so we have a system of m equations in m variables, and we need to actually solve that system of m equations. And it might be that you can't solve or you can't find a finite number of solutions to this system of m equations. There might be algebraic dependencies between the equations that would give infinitely many solutions. If you have a reduced basis of a lattice, we know that the coefficient vectors of these equations are linearly independent, but we don't know that when we turn these back into polynomials that the polynomial equations are algebraically independent. And basically, in order to get a theorem, you have to make the heuristic assumption that you will get algebraically independent equations. These are multivariate polynomials. Yeah. M. So M could be 2 or M could be 100. You can test. So the question is, basically you have this sort of black box thing where we know there's a deterministic construction where we're going to have some lattice, and this will be the coefficient vectors of like of a bunch of polynomials of this form, and then we throw this into a basis reduction algorithm, and we will just get out some essentially deterministic function of this. And if all of the equations that come out of this lattice are algebraically dependent, then we can't do anything. So.
We're not guaranteed.
Yeah, we're not guaranteed. And in general, I mean, this is a problem that comes up in every application where you try to have some kind of multivariate extension of Coppersmith's theorem, that you have to, if you're asking to get m equations out of your lattice, I don't know. There's a few specialized cases where you can prove something, but in most cases, like basically all of these papers say heuristic assumption, you can get m algebraically independent equations. In practice, in nearly all cases, you can solve the system. We did actually run into algebraic dependencies, but in a lot of cases, these resulted from some obvious sublattice, and you could still just sort of keep taking more equations and then solve it. Okay, so once you have these m equations, you say, okay, well, how am I going to actually solve this system of equations? You can, sort of use resultants to eliminate variables, or you can throw the whole thing into a Grosvenor basis reduction algorithm and try to solve it. And you might say, well, okay, isn't that slow? It'll be exponential time in the number of equations, or like doubly exponential, or whatever these things take. But in practice, if you take an over-constrained system, so you take more equations than you actually need, then it turns out to be quite fast if you have a good implementation. So this is not actually a problem. The last part that you might think about, okay, well, we had an exponential approximation factor from LLL. Is that going to be a problem? It wasn't a problem in the univariate case. It turns out that it actually is a problem in the multivariate case. And this actually results in a constraint that gives you a lower bound on the size of the approximate common divisor that you can allow. And essentially, okay, so we have some lower bound on the size of the approximate common divisor. And if you can get a sub-exponential approximation factor for your lattice basis reduction, then you can improve the lower bound on the size of the approximate common divisor. So here, if we just take an approximation factor with 2 to the dimension L, so epsilon equals 1, that gives this constraint here. If epsilon decreases, then we can get a slightly better constraint. But this is somewhat, I can go through discussing a calculation to show why this is necessary in this algorithm, but I don't actually understand in a deep way why this arises. So, but in any case, sort of here's the theorem that results. So if you want to solve the approximate common divisor problem when you have a bunch of near multiples of P, then you can solve the system of equations if you have sort of this lower bound on the size of P, and you can do so if the size of the errors is essentially the size of the multiples to the beta to the m plus 1 over m. So in the univariate case, we had m equals to 1, so we had beta squared. And so basically, as m increases, then the size of the error that we can tolerate increases, approaching the size of the common divisor. But we have a lower bound on the size of the common divisor, so if you wanted to keep decreasing the size of the common divisor and fix r, then you couldn't do that. And this algorithm runs in time polynomial in log of the inputs and exponential in the number of inputs. And if you want to assume that you don't get an exact multiple of p, but you get only approximate multiples of p, then you pay for this by changing the constant factor in the exponent. So if we try to apply this to the integer fully homomorphic encryption systems, then we get sort of an interesting phenomenon, which is that here's the set of parameters suggested by a paper by Van Dyke, Gentry, Halevi, and Vaikunthanathan. So they have a security parameter lambda, and they've set their parameters essentially so that the size of the common divisor is just slightly less than square root of log of the inputs. So this is violating the constraint that was necessary for our algorithm to work. But it's just barely violating this. So if you could do a better than exponential approximation factor for LLL, so you could do 2 to the dimension to the 2/3, then you could break this scheme in polynomial time with 3 samples. Yeah, so then you can take it slightly smaller, but then you can increase the number of samples. So for any polynomial setting of these parameters, then there's a polynomial number of samples and an approximation factor here, where you would, 2/3, 1/3, keep decreasing. So, okay, this is for sort of a theoretical setting of parameters. There was a later paper by Karan Mandal, Nakash, and Tibuchi that gave sort of concrete settings of concrete parameters for a related fully homomorphic encryption system. And if you assume an LLL approximation factor of 1.02 to the dimension, then you can just calculate the size of the lattice and the size of the inputs that you would have to just run LLL on in order to break the scheme. And essentially the dimension of the lattice, well, okay, the toy is 100-dimensional lattice. We can do that. But even in these cases, these are polynomial time algorithms, but there's no implementation that can handle an 11,000-dimensional lattice and run LLL on this. But there's no reason that you couldn't do this, just that nobody has actually scaled an implementation and gotten a big enough computer to do it. So, okay.
Will you look at the multilinear maps that we proposed from the approximation?
It's on my list, but I haven't done it yet. I think there was sort of an analysis in the paper that sort of went through just applying this sort of directly to the scheme, and it, they set their parameters so that it doesn't work. But I haven't looked at it carefully yet. Okay, so I want to talk about sort of a slightly different extension of these results. So, okay, so starting from sort of the univariate Howgrave-Graham approximate common divisors, we went to a multivariate version. Well, what if we tried to extend it in a different way? So instead of talking about integers, we talk about polynomials. So there's this sort of lovely analogy between the integers and polynomials. So on one side we have the ring of integers, on the other side we have the ring of polynomials with coefficients in some field. And basically every concept that you want to think about in the integers, you can come up with some analogous concept for polynomials. So we have some integers are primes. We can factor integers into primes. We can factor polynomials into irreducible polynomials. If we ask how big an integer is, well, the natural measure of size is an absolute value. If we ask how big a polynomial is, the appropriate measure of size that I'm going to think about is the degree of the polynomial. So if we sort of set things up the way that we want here, then everything works the way we want it to. We can divide integers. We have unique factorization. We can compute common divisors. We can do the Chinese remainder theorem, which in the polynomial side is just interpolation. I've been talking about integer lattices. You can define an analogous notion for polynomials, which is, you can think of it as a polynomial lattice. It's an FZ module. And somehow there's all these list of sort of hard problems for the integer as well. We hope that factoring is hard. The best we can do is sub-exponential time algorithms. The shortest vector problem, closest vector problem are NP hard. There's hard mathematical problems like the Riemann hypothesis. If you take the analogous problems for polynomials, they're somehow much easier. So you can factor polynomials in polynomial time. You can actually solve the shortest vector problem and closest vector problem in an FZ module in polynomial time. The algorithms are easy in a sense. And if you're sort of a serious number theorist, you can prove the Riemann hypothesis for polynomials. So what's interesting about this is somehow if you take these problems that are hard in the integers, these turn into sort of cryptographic problems. And what I'm going to show you, hopefully if I have enough time, is that if you take these analogous problems for polynomials, they turn into problems in coding theory. So I mentioned polynomial lattices. So what actually is a polynomial lattice? Sort of the concrete way to think about it is if you, in the integer case, you have vectors of integers or whatever, and you can take integer multiples of these vectors, and that generates elements in your lattice. In the polynomial case, we have vectors that are polynomials or rational functions, whatever you want. And you take polynomial multiples of these vectors of polynomials, and that generates our polynomial lattice. Then if we ask, okay, if you have a vector of polynomials, what's the length of the vector of polynomials? The definition that I'm going to take is that the length of this vector is the maximum degree of a polynomial in this vector. So using this definition, you can define an analogous notion of lattice basis reduction. I'm not going to do this here, but it's easy in a sense. And actually, there are a number of polynomial time algorithms to find shortest vectors. And the version that we care about is that we can find a vector with the guarantee that its length is 1 over the dimension times the length or the size of the determinant. So this is sort of the log analog of the guarantee that you hope you can get in the integer case. So once you've sort of set that up, then you might hope to translate the approximate GCD problem into polynomial land. And so here I've done this. Oh, actually, this is Coppersmith Theorem. No, okay, it's both. So I have some input polynomial here in the integers. Here's my input polynomial with coefficients that are polynomials in some other variable. Then I have some modulus integer. Here I have some modulus polynomial. And I'm looking for, here in the integer case, integer roots. And in this case, I'm looking for polynomial roots. And I'm hoping that I have a large GCD with my root in n. Here I'm hoping for a large GCD measured by the size of the degree. And I can do that if the size of my root is small, and here it's if the degree of the root is small.
So, just a basic question there, you're talking about regular integers or ring of integers in a number field?
Regular integers. I'll talk about the ring of integers in a number field in a couple minutes. So this is normal integers. This is normal polynomials. And what does the proof actually look like? Here's basically the steps. We're going to create some new polynomial. It's going to be a linear combination of our input polynomials. We're going to try to bound the degree. We're going to find this polynomial by constructing a polynomial lattice out of the coefficients of our input polynomials and apply lattice basis reduction.
What is it? Sorry, please.
This is the modulus polynomial. So here we have a modulus that's an integer. Here we have some polynomial that we're hoping to find roots. Yeah. Okay. So here's the steps of what we hope this, this algorithm will look like, and it checks out. So everything just works the way that you hope it does. So I've now done all this work, but I actually just said a couple slides ago that factoring polynomials is easy. And of course, you know, the reason that we were interested in Coppersmith Theorem and Howgrave-Graham's theorem is that factoring integers is hard, and so we're interested in cases where we don't have to factor integers. Well, if we can just factor polynomials, then why did we just go through all this work? It turns out that this is actually the analog of the approximate GCD problem over polynomials. Turns out to be exactly the problem of decoding ReedSolomon codes. So ReedSolomon codes are one of the most important families of error-correcting codes. They're based off of the problem of noisy polynomial interpolation. So the decoding problem for a ReedSolomon code, you're given, your input is a bunch of points, and you want to find low-degree polynomials that match your input points on a large number of values. And the classical bound for unique decoding of ReedSolomon codes gives you sort of the decoding radius is the number of points minus the degree of your, this is the dimension of your code over 2. And Guruswamy and Sudan had sort of a very amazing and famous result that if you are willing to tolerate non-unique decoding, so you're willing to tolerate sort of having a list of possible decoding polynomials for your code, then you can actually increase your decoding radius up to n minus square root of nl. So how does, you know, how is this possibly the same thing as approximate common divisors? Well, you can actually just set up the problem in a sort of similar way. So we're given these input points, and you can actually sort of translate the problem of, well, okay, we're trying to find some polynomial r that matches a bunch of these pairs. You can rewrite this polynomial matching this pair as this polynomial is r of z is actually equal to yi mod the polynomial z minus zi. So you can see that this is true. If you plug in zi, then this goes away, and we get r of zi equals yi. So this is just a rewriting of this fact. And using polynomial interpolation, we can construct some polynomial g of z that goes through all of these points. This is going to be the analog of our value a that was sort of near p. And we're going to construct our polynomial x minus g of z, which is about, or it's the analog of x minus a. And our modulus polynomial is going to be the product of z minus zi, so all of the evaluation points of our polynomial. And the degree of the GCD here actually counts the number of points where, if we evaluate f of r, this will count the number of points where r actually matches the evaluation point, or the input points. So this will match the number of non-errors in our code word. And this value measuring the size of the common divisor that we're looking for is actually telling us the number of correct points in our code word divided by the total number of points. So actually, it turns out that somehow this is almost the same as the Guruswamy-Sudan algorithm. Guruswamy and Sudan, they are also sort of, their algorithm works by constructing some interpolation polynomial Q, and instead of using lattice basis reduction, they use linear algebra over the coefficients of Q to find a solution. So in a sense, the Howgrave-Graham algorithm is replacing this linear algebra step with polynomial lattice basis reduction. And it turns out that because polynomial lattice basis reduction is so fast, this gives you a better running time than the Guruswamy-Sudan algorithm. So it's sort of interesting that the coding theorists and the cryptographers came up with the same thing at almost the same time, and sort of knew about it, but never actually managed to like lay it out exactly in parallel. So I, in the integer case, was talking about sort of multivariate extensions of the approximate GCD problem, you can try to give a sort of exactly analogous multivariate extension of polynomial approximate GCDs. And if you do that, the theorem looks something like this. So in the multivariate integer case, we had this lower bound on the size of the common divisor that we were looking for, and we had some horrible factors that arose here. In the polynomial case, because we have no exponential approximation factors for LLL, all of that horribleness goes away, and we can just get essentially that the size of the roots that we're looking for is about n to the n times beta to the n plus 1 over m. So kind of ugly, but it turns out that it's nice. The algorithm is exactly the same. Now, why do you actually care about sort of a multivariate extension of ReedSolomon codes? So in this case, instead of getting one polynomial, and we hope that we can find some low-degree polynomial that passes through a bunch of the same number of points, here we're getting a bunch of different polynomials, and we hope that we can construct polynomials, a sequence of polynomials that matches a large number of the same points for each input polynomial. And there's two versions of this. Heuristically, if you take a random sequence of polynomials and you take a random sequence of errors, then this has already come up in cryptography, that if you have a heuristic assumption, then essentially that the algebraic independence of the sequence of equations that are of the m variable equations that you get holds, then you can decode these. This works if you have random codes. But in the coding theory case, you can actually sort of define away this problem by defining your code word to have a predefined set of algebraic relationships. So you don't actually need to run into the algebraic independence problem if you're in coding theory land, where you can just say, okay, my code is defined to be this. So there's a number of constructions of codes based off of this principle, and somehow it's amazing that the coding theory world came up with these theorems, and they actually had the same result on the size of, or on sort of the multivariate approximate GCD problem, when the cryptographers were doing almost the same thing and didn't necessarily know about it. So this is interesting.
Talking about the Parvaresh-Vardy and Goswami-Rudra?
Yeah. Parvaresh-Vardy and Goswami-Rudra. So this is actually totally practical. I have a paper with Ian Goldberg and Casey Devitt where we used these multivariate ReedSolomon codes to essentially do private information retrieval. And this sort of gold line is the decoding, the running time of a decoding algorithm based off of polynomial lattice basis reduction. So this is the running time of the Goswami-Sudan algorithm. This is the running time of a heuristic decoding algorithm, and this is the brute force decoding algorithm. This is a log scale. So basically, the polynomial lattice basis reduction is incredibly fast, even in practice. It works very well. So I guess to finish up, I want to talk about a final extension of sort of these ideas to ring LWE. So instead of going from integers to polynomials, I'm going to go from integers to algebraic extensions of the integers, essentially. So the sort of setup for ring LWE, there's a lot of math here. So this would be like a whole hour-long talk in itself. But sort of waving my hands very vigorously about the math. The setup here that we're going to think about is we're going to take some ring, which is, we can look at it as two ways. We can take essentially a ring of polynomials in the variable x, mod some irreducible polynomial f of x. And we can view this ring in two ways. So we can view it as a polynomial ring, which is sort of represented as the coefficients of degree n-1 polynomials. Or we can view this as the ring of integers in the number field Q adjoin alpha, where alpha is some root of this irreducible polynomial f of x. And you can think of this ring of integers in a sort of similar way, that you have the elements of this can be represented as polynomials in alpha. So you have coefficients of these elements. So why is this problem? So why is this of interest to cryptography? It's because you can define essentially the ring LWE, ring learning with errors problem. And usually you specialize to the case where f of x, our polynomial, is x to the n plus 1. So our the alpha that we're adjoining to the rationals is some root of unity. And we're going to fix some element in this ring uniformly at random. Then the ring LWE problem is, if you're given a bunch of samples of the form some multiple of s plus some small error, small defined by some error distribution, and we're given AI and these BI sort of error-filled samples of multiples of s, then the goal is to find s. So that's ring LWE, and this is used to construct efficient public key cryptography. It's used to construct fully homomorphic encryption, and you can prove that, I guess I should have put a citation here, but it's Lubashevsky, Peikert, Regev. So the ring LWE problem is as hard as polynomial approximating short vectors in ideal lattices. Okay. So if I, from the cryptanalytics side, want to take sort of all of the Coppersmith Howgrave-Graham methods that I've been talking about and translate them over from integers to the ring of integers in a number field, what do I actually have to do? Well, okay, so instead of talking about integers, I'm going to talk about ideals. In my ring, instead of primes, I'm going to have prime ideals. In the integers, well, there's really sort of one absolute value that we care about. It's the absolute value. In a number field, you actually have n absolute values. N is the degree of your number field. Each of these comes from some different embedding into the reals. And in order to get sort of a useful theorem, you have to bound all of them. Instead of having a lattice over the integers, the analog of that is an OK module. So OK is the ring of integers. Instead of having sort of a basis, you can try to find a reduced pseudo basis of our OK module. And in this setting, in most cases, you can still do efficient arithmetic, so all the basic calculations that we need to do, even though we're dealing with algebraic numbers. So you can still find roots of polynomials and sort of represent these elements in some efficient way. So, okay, so what kind of challenges do we run into? Well, what do we do about the n absolute values? Really, the only thing that I know how to do is to keep track of them all. And this will take our lattice and it will blow it up by a factor of n. How do you, sort of skipping some details, but somehow we're going to end up with a lattice where we have ideals, and we're going to try to reduce this lattice filled with ideals in our ring of integers. How are we going to find a reduced pseudo basis? Well, it turns out that there is a polynomial time algorithm to do this, but in the case of, in sort of the univariate case, all we care about is finding a short vector in this lattice. And so it suffices to just embed each ideal as its n by n canonical embedding, which is an ideal lattice as itself. And then apply LLL to this sort of gigantic lattice that's been blown up by this factor of n. So the n by n canonical embedding is just, well, I don't really have time to talk about it, but this is an ideal lattice in itself. So we have some gigantic lattice. And then what happens, once we've blown up the size of the lattice, what actually happens to the approximation factor from LLL? In the theorem statement, it actually becomes a 2 to the n squared due to two problems. One of them is blowing up the size of the lattice by using the canonical embedding. The other factor of n comes from in the proof having to convert an arithmetic mean to a geometric mean. So somehow these are both frustrating.
And all of this is done just to solve ideal lattice specificity problem in a better way than LLM directly?
It's not better. So we're doing this just to work out what the correct analog of the approximate GCD problem is for ring LWE. So if you just take the translation of the results. So instead of having to say, well, heuristically, if you just take the ideal lattice and sort of find a short vector in it, that might not actually solve the problem. So this is a way of provably solving the problem if you could reduce the lattice.
And why is it the correct way?
It's not the correct way. I mean, because it blows up the size. So this is worse than trying to reduce the ideal lattice.
The natural way, the natural analog.
It's the natural analog of the sort of approximate GCD, like Howgrave-Graham's approach of the approximate GCD too. But it's clearly sort of not the way to actually solve this problem if you wanted to break the ring LWE-based schemes in practice. So the theorem is, okay, so we're given some number field of degree n, where n is cryptographically huge, and we're given some polynomial in with coefficients in the ring of integers in our number field, and we want to find roots of this polynomial mod some divisor of an ideal in the ring of integers. And the theorem says that we can do this if we have bounds on the size of the root, so we have to individually bound each absolute value and the product of the absolute values. So the norm of this root is 2 plus little of 1, here's the n squared over 2 times the norm of the ideal, and then we get the beta squared over d that we got all along. So you can do this in polynomial time. Probably not useful. One thing you can say is that using this theorem, if you could actually improve this approximation factor here to a 2 to the minus n times the square root of the discriminant of your number field, then this would actually solve the bounded distance decoding problem in ideal lattices in polynomial time. So in some sense, this is telling you that there's not a whole lot of hope for improving this theorem entirely, or improving the approximation factor of this theorem entirely, unless for some reason this problem isn't hard. So that was all I had. So in summary, sort of, I went from Howgrave-Graham approximate common divisors, Coppersmith Theorem, and took that in a bunch of different directions, going to multivariate versions of this theorem, going to polynomial versions of this theorem, and going to versions of this theorem over number fields. There's actually a fourth version that I didn't talk about. The analog of number fields for integers is function fields. So a finite extension of polynomials, and you can sort of do the analogous thing, and it turns out that this gives you an efficient decoding algorithm for algebraic geometry codes. So, all right, thank you. That's all I have.
Questions? Excuse me.
Yeah.
In the first talk that you saw, you had an example that trying to break an RSA, for example. You used the exponent tree.
Mm-hmm.
That was crucial to the attack. Was that crucial? Or, for example, if you use a bigger exponent like 65,000, can we apply the same attack?
No. So if you use exponent 65537, then you could find roots of size n to the 1 over 65537.
So it is crucial to be a small
Yeah.
exponent.
Yeah. So in some sense, Coppersmith's theorem is viewed as a way of cryptographically understanding small public exponent RSA.
More questions? Okay, let's thank Nadia again.